Good day. Today we're going to discuss the determinants by cofactor expansion. Now, this discussion in general, which is deal with determinants, um, we are going to study, or more precisely, study the determinants functions. Unlike real valued functions such as f of x is equal to x squared that assign a real number to the real variable x, determinant functions assign a real number f of a to a matrix variable a. Although determinants first arose in the context of solving systems of linear equations, they are no longer used for that purpose in real world applications. Although they can be useful for solving very small linear systems, say two or three unknowns, our main interest in our main interest in this discussion stems from the fact that they link together various concepts in linear algebra and provide a useful formula for the inverse of a matrix. Now, in this video, we will define the notion of the determinant. Um, this will enable us to give a specific formula for the inverse of an invertible matrix, whereas up to now, we have had only the computational procedure for finding it. Uh, this, in turn, will eventually provide us with a formula for solutions of certain kinds of linear systems. Okay, now recall from the previous discussions that we have that the 2 by 2 matrix, let's say that the matrix is, let's say our matrix would be matrix A with the elements of, let's say, A, B, C, D. Okay, is invertible if and only if this would be invertible if and only if you have the A times D minus B times C is not equal to zero, which is called determinant of the matrix A. Okay, uh, the A, D minus BC is our determinants of matrix A. Recall also that this determinant is denoted by writing, you have the determinant of A uh, is equal to, you have AD minus BC, or we could have that our A, B, C, D is equal to, you have AD minus BC. And that the inverse of the matrix A can be expressed in terms of determinant as you have the inverse of matrix A is equal to 1 over the determinant of A times you have the negative B, then you have negative C, and you have A. Okay. Now, it is important to keep in mind that the determinant of matrix A is a number, whereas the A is a matrix. Okay, now let's go to minors and cofactors. One of our main goals in this discussion is to obtain an analog for a formula of the getting the inverse of, let's say, matrix A using the determinant um, that is applicable to square matrices of all orders. For this purpose, we will find it convenient to use subscripted entries when writing matrices or determinants. Therefore, if we have a 2 by 2 matrix, we are going to write that one as like this one. Okay. So you have matrix A, and instead of A, B, C, D, we're going to have the A11 and A sub 1, 2. Then you have A sub 2, 1, and you have the A sub 2, 2. Then the two equations, uh, which is the determinant, getting the determinant, okay, will take a form of you have uh, the determinant of A, matrix A, which is you have the A11, you have the A12, A21, and A22 will have the formula A11, A22 minus A. ah, that stands for this one. So you will take a form of A11 times A22 minus A12 times A21. Now, we will define the determinant of 1 by 1 matrix A as A1. Okay, would be you have A11 the same. You have A11 the same. Now, in this case, we will have the definition, which is the key to our goal of extending the definition of a determinant to higher order matrices. Okay, so you have definition one. If A is a square matrix, then the minor entry A sub ij is denoted by Mij and is defined to be the determinant of the submatrix of the submatrix that remains after the ith row and j column are deleted from A. The number -1 raised to I plus j m sub ij is denoted by C sub ij and is called the cofactor of entry I sub uh, A sub ij. Okay. Uh, for example, we have finding minors and cofactors. So let's say that our matrix A, you have you have 3, 1, -4, 2, 5, 6, 1, 4, 8. Now take note that we have followed the standard convention of using capital letters to denote minors and cofactors, even though they are numbers and not matrices. Okay. Now let's say that we are going to have the minor of entry uh, A sub 1 1. Okay. Meaning that if that would be the case, you have entry uh, A sub 1 1, we are going to have something like this. So our minor sub 1 1, take note that our matrix would be 3, 1, negative 4, then 2, 5, 6, and 1, 4, 8. Now, what we are going to do here is we are going to delete the row and the column where the uh, A sub 1 1 is located. So, in this case, okay, we are going to delete this and delete this one. Okay, so what will happen is that you will now have the uh, new matrix 5, 6, 4, 8, in which if we are going to solve the determinant of these matrix, the new matrix, the 5, 6, 4, 8, the determinant would be 16. So that's the minor uh, 1, 1. Now, the cofactor of A sub 1, 1, you have the C uh, sub 1, 1. We are going to have the formula negative 1 raised to 1 plus 1 m 1 1, which is equal to m 1 1, which is equal to 16. Okay. So similarly, okay, the minor entry of, let's say, 3 2. Okay. So the minor of 3 2. So take note that our matrix, we have 3, 1, negative 4. Then you have 2, 5, 6. Then you have 1, 4, 8. Now, what you are going to do, what we are going to do here is we are going to locate the uh, 3, 2, the A sub 3, 2, which is uh, the column and the row. Okay, so our new our new matrix would be, you have 3, negative 4, then you have 2, 6. And if you are going to get the determinants of that one, that's equal to, you have 26. Okay, that's the minor entry of uh, A sub 3 2. And then if you are going to have the cofactor of A sub 3 2, you have negative 1 raised to 3 plus 2 times the uh, minor of A3 2, which is equal to negative um, minor of 3 2, which is equal to negative 26. Okay, so in this, now take note that the term determinant okay, was first introduced to us by the German mathematician Carl, Carl Friedrich Gauss in 1801, who used the term to who used them to determine properties of a certain kinds of functions. So interestingly, the term matrix is derived from a Latin word for womb because it was viewed as container of determinant. And then the term minor is apparently due to the English mathematician um, James Sylvester, okay, who wrote the following in the paper published in 1850. Okay, so let's have the definition of general determinant. Okay, so we have theorem 2.1.1. If A is an n by n matrix, then regardless of which row or column of A is chosen, the number obtained by multiplying the entries in the row or column by the corresponding cofactor and adding the resulting product is always the same. Okay, so this results allows us to make this definition. So in definition 2, if A is a n by n matrix, then the number obtained by multiplying the entries in any row or column of A by the corresponding cofactors and adding the resulting products is called the determinant of A. The sum themselves are called cofactor expansion of A. That is, you have the determinant of A is equal to A sub ij, A sub 1j rather, times the cofactor 1j plus A sub 2j times the cofactor, okay, of cofactor sub 2j plus so on, plus you have the A sub nj times the cofactor nj, okay, and which is called the cofactor expansion along the j column. And the determinant of A is equal to, again, you have the uh, A sub I1 times C sub, or the cofactor of the I1 plus A sub 1, I2 rather, times the cofactor I2 plus so on plus uh, I sub n times the cofactor I sub n, which is also called as the cofactor expansion along the I row. Okay, let's have an example of the cofactor expansion along the first row. So for example, you have that matrix. You have 3, 1, 0, negative 2, negative 4, 3, 5, 4, negative 2, and we are going to find the determinant of that matrix by cofactor expansion along the first row. Okay, so for our solution, so you have the determinant of A, okay, is equal to, take note that you have a 3, 1, 0, negative 2, negative 4, 3, 5, 4, negative 2. Okay. Then you have the, what you call this one? The uh, first row. Okay, so you have 3, okay, times you have negative 4, 3, 4, negative 2, okay, times negative 1, you have negative 2, 3, 5, negative 2, plus you have 0, negative 2, negative 4, 5, and 4. Okay, which is equal to, in this case, so you have 3 times the determinant of this is, you have negative 4 minus 1, okay, times the determinant of this is, you have negative 11 plus, of course, any number multiplied by 0 is 0, which is equal to negative 1. Okay, so the determinant of A is actually equal to negative 1. Okay, so let's have another example. Here we have the smart choice of row or the column. So if A is the 4 by 4 matrix, which we have that one, find the determinant of A. To find that determinant, it will be easiest to use the cofactor expansion along the second column since it has the most zeros. Okay, the second column. So you have, in this case, you have the uh, determinant of A is equal to, in this case, you have 1 times, you have the 1, uh, 0, negative 1, then you have 1, negative 2, 1, and 2, 0, 1. Okay, now for the 3 by 3 determinant, it will be easiest to use cofactor expansion along its second column since it has the most zeros. So in this case, the determinant of A is actually, you have 1 uh, times, you have negative 2 times, you have 1, negative 1, 2, 1. Okay. Then you have here negative 2 times 1 plus 2, which is equal to negative 6. Okay. So let's have the determinant of an upper triangular matrix. Okay. So the following computation shows that the determinant of a 4 by 4 upper triangular matrix is the product of its diagonal entries. So each part of the computation uses a two-factor expansion along the first row. So if you have this one, then you have the A sub 1 1 times, you have the cofactor A 2 2, then you have 0 0, then you have A A32, A330, then A42, A43, and A44. And then since this is 3 by 3, then you have uh, A11 times A22, then you have here A320, then A43, A44, okay, which is equal to, you have A11, A22, A33 times uh, A44, which is equal to A11, A22, A33, A44. Okay. Okay. So in this case, okay, we can now have the theorem 2.1 sub 2.1.2. If A is a n by n triangular matrix, which can be upper triangular, lower triangular, or diagonal, then the determinant of A is the product of the entries on the main diagonal of the matrix. That is, the determinant of A is equal to A sub 1 1 times A sub 2 2 up to A sub n n. Okay. So we have the useful techniques for evaluating 2 by 2 and 3 by 2 determinants. So the determinants of 2 by 2 and 3 by 3 matrices can be evaluated very efficiently using the pattern that is uh, this one. Okay. So you have for the 2 by 2, you have the uh, A sub 1 1, A sub 2 2, then you have the A 1 2, A 2 1. And for the 3 by 3, you are just going to expand, okay, the matrix. So the in the 2 by 2 case, the determinant can be computed by forming the product of the entries on the rightward arrow and subtracting the product of the entries in the leftward arrow. In the 3 by 3 case, we first recopy the first and second column as shown in that figure, after which we can compute the determinant by summing the product of the entries in the rightward arrows and subtracting the products on the leftward arrows. These procedures, okay, execute the computations which agrees with the cofactor expansion along the first row. Okay, so we have to bear in mind that the arrow technique only works for the determinants of 2 by 2 and 3 by 3 matrices. Okay, so let's have example. So technique for evaluating 2 by 2 and 3 by 3 determinants. So for the first, you have the 2 by 2, the matrix 3 1 4 negative 2. So in this case, of course, so you have um, 3 1 4, negative 2. So in this case, you have this one and this one, which is equal to, you have 3 times negative 2 minus, you have 1 times 4, which is equal to negative 10. So for in this case, we are just going to expand. So you have 1, negative 4, 7, 2, 5, negative 8. Then you have 3, 6, 9. Then extend, you have the 1, negative 4, 7. Then you have the 2, 5, negative 8. Then of course, you have this one. And you have this one. And you have this one. Then you have this one, 3 here. This and this one. Okay. So what you have here is, you get the product. So you have um 45 plus, you have 84 plus 96. Okay. Minus, you have 105 minus 48 minus 72, which is equal to 240. So we have, for this video, we have discussed the determinant, the minor, the cofactor, and the cofactor expansion. So it is expected that you can find the minors and cofactors of a square matrix, use the cofactor expansion to evaluate. So use the cofactor expansion to evaluate the determinants of a square matrix, and then you can use the arrow technique to evaluate the determinants for the 2 by 2 or 3 by 3 matrix, and then use the determinant of 2 by 2 invertible matrix to find the inverse of that matrix, and of course you have find the determinants of the upper triangular, lower triangular, or diagonal matrix by, of course, by inspection. So I hope you got all those skills. So with that, uh, thank you very much for listening.